Welcome back. In our last episode, we dove into recent techniques like low-rank adaptation, or low-raw, that streamline model adaptation, especially for large language models. Low-raw's approach to reducing parameter and resource requirements was fascinating, wasn't it?
Absolutely. It really showed how much efficiency matters, especially when working with large-scale models. And I think that's what makes today's topic so interesting. It gives us a foundation for understanding models that can access external information dynamically.
Exactly. Today, we're stepping back a bit to explore earlier research with Retrieval-Augmented Generation, or RAG, which takes a different approach to knowledge management. Unlike low-raw, which focuses on internal efficiency, RAG uses an external memory module. This way, it taps into relevant data on the fly, retrieving information rather than relying solely on what's stored in the model parameters.
That's really intriguing because RAG is like having a reference library at hand, while low-raw optimizes what's already in the head, so to speak. So with RAG, we're looking at a method that brings in specific factual data as needed, which I think is essential for knowledge-intensive tasks.
And that's part of RAG's significance. It not only combines a parametric memory, which stores knowledge within the model, with a non-parametric, retrieval-based memory, but also uses dense vector indexing to fetch relevant, up-to-date information. This hybrid memory system is particularly impactful for NLP tasks that need contextually rich, accurate responses, like open domain question answering or fact verification.
So, besides being a natural fit for question answering, RAG's flexible setup means it could be applied to various NLP tasks, right? And from what I understand, it's capable of updating its knowledge without needing a full retraining, which is a big plus for tasks needing real-time accuracy.
Absolutely. Imagine a model that can verify facts and adapt its knowledge base without having to go through the heavy process of retraining. RAG's approach lets it fetch and verify sources, offering a kind of document provenance, a big step forward in generating trustworthy and current information.
I can see how that aligns well with what we've been discussing about resource-conscious models. It's like RAG bridges the gap, giving models both flexibility in tasks and efficiency in updates.
Exactly. So in today's episode, we're going to cover how RAG achieves these outcomes, starting with its hybrid memory setup, moving through the retrieval mechanisms it uses, and then looking at its impact across different applications like open domain QA, fact verification, and more. Ready to get into the specifics?
Definitely. Let's explore how RAG works in practice.
All right, let's take a look at the abstract. This section primarily outlines the purpose and innovations of the RAG model, which stands for Retrieval-Augmented Generation. Essentially, it focuses on how large language models, while effective, struggle with certain limitations, like precisely manipulating or retrieving specific knowledge. So RAG introduces a blend of pre-trained memory and retrieval-based approaches to overcome these issues. Let's dive into the core points of how RAG addresses this.
So, the main idea is to combine two types of memory, one that's pre-trained and one that can be retrieved or updated as needed.
Exactly. The abstract highlights that traditional pre-trained models store knowledge in parameters, which means their knowledge base is fixed once training ends. RAG, on the other hand, adds what's called non-parametric memory, meaning it can access external sources for updated or additional information. For this, it uses dense vector indexing of resources like Wikipedia, allowing it to recall facts on the fly and potentially even update its knowledge base without retraining.
Got it. So, it's like combining a brain with a searchable database. But why does this help specifically with knowledge-intensive tasks?
Good question. The abstract points out that in knowledge-heavy tasks like answering specific factual questions or generating diverse content, having access to retrievable memory allows for more precise, reliable, and varied responses. This is especially useful in cases where static models might struggle to recall rare facts, or might even hallucinate answers that sound plausible but aren't accurate.
I see. And does RAG improve upon previous models that tried using non-parametric memory?
Yes, the abstract mentions that while earlier models like ReL-M and ORQA could integrate retrieval-based memory, they mostly focused on simple question answering. RAG extends this by applying its retrieval capabilities to more complex generative tasks. That's an advancement because it integrates both types of memory more flexibly, supporting a broader range of language generation and answering tasks.
Interesting. And how does RAG perform on these tasks?
RAG actually sets new benchmarks on various open domain QA tasks, surpassing previous models like parametric-only seek-to-seek or retrieve and extract architectures. Its combined memory allows it to generate responses that are not only accurate, but also more specific and contextually relevant than what a static model might produce.
So, the abstract concludes that RAG offers both improved factual accuracy and response diversity. Does it say anything about future implications or broader impacts?
Yes, it does. It briefly touches on how the non-parametric memory can be updated as the world changes, meaning RAG could potentially adapt to new information without being retrained from scratch. This is beneficial in fields that require up-to-date knowledge or evolving facts. In summary, the abstract gives us a glimpse into how RAG tackles the limitations of traditional language models, blending static knowledge with adaptable retrieval. This allows for a wider range of applications and more trustworthy outputs in complex language tasks. And that wraps up the abstract. Now let's ease into the first section, the introduction, where the purpose and goals of the RAG model are laid out in more detail. In the introduction, the authors discuss a significant challenge with traditional language models. While they can store a lot of factual knowledge, they have trouble retrieving and managing that knowledge accurately. This leads to issues in tasks requiring precise information, often resulting in what's called hallucination, where the model generates plausible-sounding but incorrect information. So, the purpose here is to introduce the RAG model as a way to tackle these issues.
So, it sounds like RAG is designed to reduce hallucinations by adding a way to retrieve factual information as it generates responses. Is that right?
Exactly. The introduction highlights that while pre-trained models can learn and generate coherent language, they're limited by the knowledge stored within their parameters. RAG combines traditional pre-trained or parametric memory with an external non-parametric memory, essentially a retrieval system linked to a knowledge source like Wikipedia. This addition aims to make RAG's responses more factual by grounding them in real data that can be updated or expanded.
Interesting. So, by using external sources, RAG avoids having a fixed memory, right? Meaning it can add new facts without retraining the whole model?
Precisely. This is a crucial benefit because it means RAG can adapt to new information simply by updating its external memory. The introduction contrasts RAG with past retrieval-based approaches like ReLM and ORQA, which also used external memory but were limited to simpler tasks, primarily focused on question answering.
That makes sense. By broadening the use of non-parametric memory, RAG can take on more complex language tasks than those earlier models. Does the introduction also discuss any expected outcomes or improvements over previous methods?
Good point. Yes, it does. The authors expect RAG to perform better on various knowledge-intensive tasks, not only by accurately retrieving information, but also by improving response quality overall. By pairing retrieval with generative capabilities, RAG should generate text that is more specific, diverse, and less prone to factual errors. The introduction sets up the expectation that RAG will outperform closed-book models, those without retrieval, for open-domain tasks.
It seems like this hybrid approach is the best of both worlds. It offers flexibility in knowledge access and boosts factual accuracy in generated responses.
Absolutely. And that's the central idea the introduction puts forward. The RAG model stands as an innovative step in balancing static, pre-trained knowledge with the dynamic potential of non-parametric retrieval, making it highly suited for tasks that require accurate, up-to-date information. So with this foundation, the introduction makes it clear why RAG could represent a major advance in retrieval-augmented generation. All right, that covers the introduction. Now let's move into the models section, where we'll look at the specific approaches used within RAG. This part lays out the mechanics of how RAG combines both retrieval and generation components, especially with the two main variants of the model, RAG sequence and RAG token. In this section, the authors introduce the two main versions of RAG, each offering a unique way of incorporating retrieved documents into the text generation process. The first is RAG sequence. Course. This version uses a single retrieved document to guide the generation of an entire sequence. The idea is to marginalize over this document as a latent variable, so the model retrieves the top K documents, but uses just one of them consistently throughout generation.
So with RAG sequence, the model sticks to one document for the full answer. It seems like that might keep the response coherent since it's based on one source.
Exactly. By relying on one document, RAG sequence can maintain a consistent context. The model's probability for generating each word in the answer depends on both the input query and this chosen document. It's like taking one specific reference to ensure the output stays focused and aligned.
Got it. And I assume RAG token works differently by using multiple documents somehow?
Yes, that's right. In RAG token, each word in the generated answer could technically come from a different retrieved document. Instead of using a single document for the whole answer, the model can shift its reference document for each token, which allows it to draw from a mix of top retrieved sources. This adds flexibility, especially for complex answers requiring diverse information.
So RAG token might be better for more complex responses where multiple sources are helpful. But wouldn't switching documents create coherence issues in the output?
That's a good point. With RAG token, there's always a balance. While it allows richer and potentially more accurate responses by drawing from different documents, the model has to manage coherence, making sure the response doesn't feel disjointed. Each token generation step marginalizes over a new top K document set, which can add diversity but requires careful tuning for clarity.
Interesting. And both versions use this marginalization approach over the retrieved documents. Does the model still choose the best tokens based on a probability score?
Exactly. Both RAG sequence and RAG token use probability calculations to weigh the relevance of the retrieved documents, ultimately generating the most probable answer sequence based on the retrieved content. This marginalization is part of what makes RAG unique, because it can weigh multiple sources dynamically, either over a single document or across several documents for each token. To sum it up, the RAG sequence model prioritizes consistency by sticking to one document for the response, while RAG token brings in flexibility, pulling relevant information from several documents as needed. Both have their strengths depending on the nature of the task and the type of response required. Now that we've covered the RAG models, let's go into the retriever and generator components, starting with dense passage retrieval, or DPR, as the primary retrieval method. This approach is particularly effective at finding relevant documents for input queries. The DPR component in RAG uses what's called a bi-encoder architecture, which includes two BERT-based encoders, one for documents and one for queries. When a user asks a question, the DPR retriever converts it into a dense vector representation, then searches for similar document vectors in a large index like Wikipedia. This setup lets the RAG model retrieve relevant documents quickly and accurately.
So, both the question and documents get turned into these dense vectors. That must help the retriever identify the most relevant information even if the wording is different, right?
Exactly. By transforming everything into dense vector representations, DPR can match semantically similar content, even if exact word matches are missing. It's especially useful for open domain tasks where users might phrase questions in many different ways. The retriever narrows down the top documents, and then these are passed to the generator.
That makes sense. And if DPR retrieves multiple documents, how does RAG decide which parts to use for generating the answer?
Good question. RAG uses the generator, BART, to interpret and combine information from the retrieved documents. Essentially, BART is a seek-to-seek transformer model designed to generate coherent answers based on both the original query and the retrieved content. It's flexible enough to handle different types of input data, including cases where it has multiple documents to work with.
I see. So, BART is in charge of actually crafting the response based on the retrieved documents. Why was BART chosen specifically for this task?
BART is particularly well suited here because it was pre-trained on various language tasks with a denoising objective. Basically, it's practiced at understanding and completing sequences, even when they contain gaps. This pre-training helps it maintain coherence in generated responses. In RAG, BART combines the query and retrieval results to produce more precise and contextually relevant answers, leveraging its strong generative capabilities.
So, with DPR for retrieval and BART for generation, RAG is set up to both find relevant information and deliver a coherent, factually supported answer. Is there any specific way BART processes the retrieved documents to integrate them with the query?
Yes, RAG concatenates the retrieved document content with the input query before passing it to BART. This way, BART gets a single, cohesive input that includes the original question and the most relevant information from DPR. This design lets RAG treat each retrieved document as additional context, boosting the chances of generating a well-informed answer. To sum up, the DPR retriever is key for locating relevant information quickly, while BART takes on the role of synthesizing that information into coherent, contextually accurate responses. Together, they make RAG capable of high-quality retrieval-augmented generation. Having explained the models and their components, let's talk about how RAG is trained and how it decodes responses during inference. This section dives into the mechanics of fine-tuning the retriever and generator together to get the best results. For training, the authors use an approach where the retriever and generator are trained jointly, but without specific guidance on which document to retrieve for each query. Instead, the model is fine-tuned on a set of input-output pairs, which allows it to learn which documents are likely to contain useful information. The training goal is to minimize the negative marginal log likelihood of each target output. They use stochastic gradient descent with the Atom optimizer to achieve this.
So, there's no preset answer key telling the model which document to choose. It just learns by refining its choices as it minimizes this loss?
Exactly. The model doesn't get told which document is the best. It learns from context and target pairs. Interestingly, the authors decided not to update the document encoder because it would require constantly updating the document index, which is quite resource-intensive. Instead, only the query encoder and the BART generator are fine-tuned.
That must save a lot of computational resources. And I guess since the document index isn't changing, the retriever has a stable reference point throughout training.
Yes, that's right. Keeping the document encoder fixed also helps maintain efficiency without sacrificing performance, according to the authors. Now moving on to decoding. This is where RAG sequence and RAG token require different techniques to decode answers during test time. For RAG token, which can use different documents for each token in a response, the model marginalizes over the top k-retrieved documents. Each token is generated based on a weighted probability across these documents.
That makes sense for RAG token since it uses multiple sources. But what about RAG sequence? Does it work the same way?
Good observation. RAG sequence is a bit different. Since it uses one document for the entire response, it doesn't marginalize at each token. Instead, it runs a beam search for each document and scores the hypotheses based on the document's overall fit with the query. This process is called thorough decoding, where the model evaluates all options, but it can be resource-heavy for longer responses. They also propose fast decoding, an efficient approximation that skips additional forward passes once a set of candidates is generated.
So, thorough decoding goes deep but can take longer, while fast decoding sacrifices a bit of accuracy for quicker results. Sounds like each approach has its ideal use cases depending on time and resource constraints.
Exactly, you've got it. In summary, the training process allows RAG to refine its retrieval and generation without explicit retrieval guidance, while the decoding methods balance accuracy and speed based on task requirements. All right, now that we've discussed the training and decoding, let's move on to RAG's performance on question-answering tasks, both in open domain and abstractive formats. This part of the paper really highlights RAG's flexibility and strengths. In the open domain question-answering section, the authors describe how RAG performs across several well-known QA datasets. These include natural questions, trivia QA, web questions, and curated trek. The goal here is for RAG to generate answers without specific training on those datasets, leveraging only its retrieval and generative abilities. RAG's design allows it to outperform many extractive approaches, which traditionally retrieve and directly extract information, as well as closed-book models, which rely only on parametric memory.
So in open domain QA, RAG essentially uses its retriever to find relevant documents and then generates an answer based on that. This makes it better suited for answering a wider variety of questions than closed-book models?
Exactly. RAG's retrieval-augmented approach gives it access to a much larger set of potential answers, which significantly improves accuracy for open domain questions. By retrieving and generating rather than simply extracting, RAG can provide more nuanced answers. For example, if relevant documents provide only partial information, RAG can still generate a complete answer by synthesizing these details, something extractive models might struggle with.
Got it. And then there's the abstractive QA task, which I assume goes even further by requiring RAG to create new phrasing based on what it retrieves.
Yes, that's right. In the abstractive QA task, RAG generates answers in its own words, making it an advanced form of natural language generation. The authors used the MS Marco dataset to test this, a task where RAG had to produce free-form responses based on retrieved passages. Interestingly, in cases where Wikipedia alone doesn't provide enough information to match a reference answer, RAG combines its parametric memory with the non-parametric retrieval to craft reasonable, contextually accurate responses.
So, if I understand correctly, RAG's performance in abstractive QA showcases its ability to generate unique answers that aren't just rephrased content from one source but are created from multiple clues in different documents.
Exactly. And that's a core strength of RAG. It can handle questions where the exact wording isn't in any one document, which is valuable in abstractive QA. This section effectively demonstrates how RAG can outperform both retrieval-only and generation-only models by blending the best of both approaches, resulting in a more accurate and comprehensive response capability. In summary, RAG, flexibility in both open domain and abstractive question answering tasks, shows its strength as a model that can retrieve and generate nuanced, complete answers, setting a new standard for QA tasks. We've now covered open domain and abstractive question answering. Moving forward, we'll look at some unique applications of RAG, including generating Jeopardy-style questions and fact verification, which push the model's retrieval and generation abilities even further. In the Jeopardy question generation task, the goal is to create questions based on answer entities in a Jeopardy format. Jeopardy questions are often complex, requiring two pieces of information to identify the answer, and RAG is tasked with generating these knowledge-intensive questions conditioned on specific answer entities. The challenge here is for the model to phrase the question in a way that uniquely points to the correct answer. RAG was evaluated against BART using the QBLEU1 metric, which is designed to better capture entity relevance in generated questions.
So, in this case, RAG isn't retrieving answers but rather generating questions based on provided answers. Does it perform well compared to BART?
Yes, RAG outperformed BART in both factuality and specificity. In a human evaluation, RAG produced questions that were more aligned with factual details and included unique information tailored to the answers. RAG token, in particular, stood out because it could pull from multiple documents to gather supporting details for generating these complex questions. This capability makes it ideal for generating questions that need more than a single source of information.
Interesting. So, RAG token's approach of combining multiple sources helps it generate better, more informative Jeopardy questions compared to single document models.
Now, in the fact verification task, RAG's role shifts from generation to classification. This task uses the Fever dataset, where the model has to decide if a claim is supported, refuted, or not enough information based on retrieved Wikipedia evidence. Believe. It's a test of the model's retrieval and reasoning abilities, because it not only has to retrieve relevant content, but also determine if that content substantiates or contradicts the claim.
So, It's not about just finding relevant documents, but actually reasoning over them to judge if they back up the claim. How does RAG handle this?
RAG performs quite well, achieving results within 4% of specialized fact-checking models that require retrieval supervision. RAG is unique here because it doesn't rely on manually labeled retrieval supervision during training. It uses its retrieval component dynamically, which makes it more adaptable and practical for real-world verification tasks, where supervised retrieval data isn't always available. To wrap up, in these two diverse tasks, Jeopardy question generation and fact verification, RAG showcases its flexibility and effectiveness. It can creatively generate knowledge-based questions and accurately verify factual claims, all without strict retrieval supervision, making it a powerful tool for both question generation and fact-checking applications. All right, now that we've gone over some of RAG's applications, let's dive into the results of how RAG performs specifically in open domain and abstractive question answering tasks. This section provides a comparison of RAG with other models and highlights some key outcomes. In open domain question answering, RAG was tested against datasets like natural questions, trivia QIA, web questions, and curated Trek. These are widely used benchmarks for evaluating a model's ability to answer diverse, fact-based questions. The results showed that RAG outperforms traditional extractive QA models and closed-book models, which only rely on internal knowledge without retrieval. By combining retrieval and generative abilities, RAG achieved a new state-of-the-art on several of these datasets.
So, RAG's use of both retrieval and generation helps it outperform models that only extract answers from documents or only generate from memory. That's impressive.
Exactly. RAG's retrieval-augmented approach gives it access to a wide pool of information while still generating coherent, contextually relevant answers. One interesting outcome was that RAG could even generate correct answers when the retrieved documents didn't contain the exact answer, something purely extractive models couldn't achieve. This capability adds robustness to the model's performance across various types of questions.
That's really useful. And how did RAG perform on the abstractive question answering task?
In abstractive QA, RAG was evaluated on the MS-Marco dataset, which involves generating free-form descriptive answers. Here, RAG sequence outperformed the BART model by 2.6 points on the BLU and Rouge-L scores, which measure the quality and relevance of the generated answers. What makes this result significant is that RAG performed well without access to gold or directly relevant passages, relying solely on Wikipedia and its parametric memory to fill in the gaps.
That's impressive. RAG can essentially create relevant, contextually accurate responses even when it doesn't have direct access to certain answers. I'm guessing this ability helps reduce hallucinations as well.
Absolutely. RAG models were found to hallucinate less frequently than BART, generating answers that are not only more factual but also diverse in wording. This was especially important for tasks where exact matching answers weren't always possible from Wikipedia alone. So, RAG's ability to leverage both retrieval and memory became an advantage. In summary, RAG's results in both open domain and abstractive QA demonstrate its strengths in creating reliable, varied answers and handling diverse information needs, showcasing why it's so effective in knowledge-intensive tasks. All right, let's shift our focus to RAG's performance in generating Jeopardy-style questions and verifying factual claims. These two tasks highlight how well RAG can handle both complex question generation and classification-based verification. Starting with Jeopardy question generation, this task challenges RAG to create questions based on provided answer entities. For instance, given an answer like the Divine Comedy, RAG needs to generate a question that uniquely points to this answer, such as, this 14th century work by Dante is divided into 3 parts: Inferno, Purgatorio, and Paradiso. The model's ability to combine multiple pieces of information into a coherent and factually specific question is tested here.
So, this requires more than just simple question generation. RAG has to integrate multiple details to ensure the generated question aligns specifically with the answer. How did it perform on this task?
Token performed particularly well, outperforming both BART and RAG. Sequence in QBLU1 scores, which emphasize entity relevance. Human evaluators found RAG-generated questions more factual and specific. Into that. In fact, RAG was rated as more factual than BART in 42.7% of cases, while BART was preferred in only 7.1% of cases. This highlights RAG's ability to handle knowledge-intensive question generation better than a single document approach.
That's impressive. And RAG token's use of multiple documents probably helps it include those extra details that make the questions more specific and unique.
Exactly. By accessing various documents, RAG token generates questions that are not only accurate but rich in contextual information, which is ideal for Jeopardy-style prompts that rely on layered facts. Now moving to the fact verification task. RAG is tested on the fever dataset to verify whether claims are supported, refuted, or lack enough information based on retrieved evidence from Wikipedia.
So here, RAG isn't generating text but making a classification based on retrieved information. How does it compare to models specifically designed for fact-checking?
RAG performs quite well, scoring within 4.3% of state-of-the-art models on Fever's three-way classification task. Importantly, RAG doesn't require retrieval supervision, unlike many specialized fact-checking models. This means RAG can verify claims without needing training that specifies which documents to retrieve for each claim, making it more versatile for real-world applications where retrieval guidance may not be available. In summary, these tasks show RAG's adaptability, excelling in both knowledge-rich question generation and accurate fact verification. Its unique approach to retrieval and generation makes it well-suited for diverse applications requiring specific and reliable information. Now that we've covered RAG's main applications and performance, let's go over some additional results that provide more insights into the model's unique capabilities, particularly around diversity and retrieval flexibility. In this section, the authors discuss how RAG models, especially RAG sequence, are able to generate more diverse responses compared to other models like BART. They measured diversity by calculating the ratio of unique n-grams in generated responses, showing that RAG's output contains more varied phrases and word combinations, particularly in RAG sequence responses.
So, RAG sequence ends up with more distinct expressions or phrases. I suppose that would make it more adaptable in conversational or generative tasks?
Exactly. This diversity is a valuable trait for tasks that benefit from creative or varied language, making responses feel less repetitive. Another interesting finding was that freezing the retriever during training, as part of an ablation study, showed a clear drop in performance across tasks. This confirms the importance of joint training for enhancing retrieval precision and relevance.
Right. Since training the retriever dynamically allows it to fine-tune its ability to pick the best documents for each query. Did they look at the impact of different retrieval methods as well?
Yes, they did. They compared RAG's dense retriever to a traditional word overlap-based method called BM25. While BM25 performed relatively well on the entity-heavy fever dataset, RAG's dense retrieval method outperformed BM25 on other tasks, showing the advantages of a more nuanced, semantic approach to retrieval for diverse information needs.
It seems like RAG's dense retrieval approach better captures the meaning behind queries rather than relying solely on exact word matches.
Exactly. Additionally, they explored the concept of index hot swapping, which highlights a unique advantage of RAG's non-parametric memory. By swapping out the document index with a different Wikipedia dump, the model could adapt its knowledge without retraining, effectively updating its world knowledge base for time-sensitive tasks. This flexibility isn't possible with parametric-only models like T5, which would require retraining. In summary, these additional results underscore RAG's versatility. not only in handling a variety of language tasks, but also in maintaining diversity, retrieval efficiency, and knowledge flexibility, positioning it as a powerful tool for dynamic, information-rich tasks. Now that we've reviewed the core results of RAG-S performance, let's take a look at some related work that has paved the way for retrieval-augmented generation, along with some advancements in memory architectures and retrieval methods. The authors in this section highlight key advances in single-task retrieval models, which have shown that retrieval improves performance across a range of isolated NLP tasks. These include open domain question answering, fact-checking, and Wikipedia article generation, among others. Traditional retrieval-based systems focused on each of these areas individually, but RAG's contribution is in unifying these into a single architecture capable of high performance across various tasks.
So, instead of building a new retrieval model for each task, RAG offers a flexible framework that can be applied to different NLP applications. That sounds efficient.
Exactly. The idea of a unified, retrieval-augmented approach is a significant shift, moving from task-specific retrieval to a general-purpose retrieval-augmented framework. This stands in contrast to earlier general-purpose models like GPT-2 or BART, which, while versatile, did not incorporate retrieval to address knowledge-intensive tasks directly. RAG instead pairs retrieval with generation, allowing it to handle tasks requiring complex and updated information.
Right. So models like GPT-2 or BART were versatile but limited to the knowledge they had at training time, while RAG extends that by pulling in external, up-to-date data. And I assume RAG builds on advances in learned retrieval as well?
Correct. There's been substantial progress in learned retrieval techniques, especially with neural language models that can adjust their retrieval for specific tasks. Some earlier approaches used retrieval modules optimized for single tasks, like question answering. RAG builds on these by combining a differentiable retrieval module, DPR, with a generative model, BART, creating a flexible setup that can adapt to new queries by retrieving relevant documents on the fly.
And what about memory-based models? I know some architectures use memory to store information explicitly. Does RAG relate to those models in any way?
Great question. Yes, RAG shares similarities with memory-based architectures that use large, external memories accessible by neural networks. However, traditional memory networks often relied on dense embeddings or fact embeddings, which made them challenging to interpret or update. RAG-S memory, on the other hand, is based on raw text from Wikipedia. This approach makes RAG's memory more transparent and easier to update, as it can simply swap out or add new documents. In summary, RAG represents an evolution from task-specific retrieval and static memory-based architectures to a dynamic, interpretable framework that brings together retrieval, memory, and generation. It builds on the successes of prior models but expands the possible applications and adaptability of retrieval-augmented language generation. With a good understanding of RAG's comparisons and related methods, we can now move into the discussion section. Here, the authors summarize the primary findings and potential areas for future work on retrieval-augmented generation models. In this work, the authors emphasize that RAG has set new benchmarks in open domain question answering by combining parametric and non-parametric memory. They highlight how RAG-S outputs are generally more factual and specific compared to purely parametric models like BART, which lack the retrieval-based, non-parametric memory. By examining the learned retrieval component, they validate its effectiveness in refining answer generation and minimizing hallucinations by grounding outputs in actual sources. This grounding not only improves accuracy, but also enhances interpretability and transparency.
So, RAG-S non-parametric memory actually helps reduce hallucinations. And at the same time, it makes the model's answers easier to verify or trace back to a source.
Exactly. The authors also highlight the flexibility RAG gains from using a retrievable index that can be updated independently of the model's training. This is called index hot swapping, which allows RAG to stay current by updating its knowledge base, especially useful for time-sensitive information. Unlike parametric models that require retraining to incorporate new information, RAG can adapt just by modifying its retrieval index.
That's quite practical. And it seems like a promising approach for any field that needs up-to-date information without the cost of frequent retraining.
Exactly right. Looking forward, the authors suggest that a potential direction for further research could be exploring joint pre-training of both the retrieval and generation components from scratch. By aligning these two components more closely from the beginning, RAG could enhance its performance on tasks where both retrieval and generation play critical roles. They mention considering objectives similar to Bard's denoising, which could support better retrieval condition generation, or even experimenting with new training objectives specifically designed for knowledge-intensive tasks.
So, future research might focus on making RAG even more cohesive by jointly training retrieval and generation. That sounds like it could lead to a more seamless model for complex tasks.
Yes, exactly. The discussion concludes with the authors reflecting on how RAG opens up new avenues for combining parametric and non-parametric memories in NLP, which could lead to applications across a wider range of language tasks. The combined strengths of these memories offer an adaptable and powerful framework, setting the stage for future advancements in retrieval-augmented generation. Well, that wraps up our deep dive into RAG and its hybrid memory approach. We've covered a lot today, from RAG's dynamic retrieval system to its impressive flexibility across tasks like question answering and fact verification.
Yeah, and I think it's fascinating how RAG combines both parametric and non-parametric memory. The ability to retrieve real-time information while maintaining model accuracy is such a game changer.
Absolutely. And that provenance feature, where RAG can point back to document sources, is another standout. It really adds a layer of trustworthiness to the model's outputs.
Agreed. It's definitely a strong foundation for models that need both efficiency and adaptability, especially when knowledge is constantly evolving.
Exactly. Well, thanks to everyone for tuning in and joining us on this journey into the world of retrieval-augmented generation. We hope you found it as engaging as we did.
Yes, thanks for listening. Looking forward to next time.